So hello everyone, today I will be explaining about our project that is distributed EHR system. So let us first look at our architecture. So the very first thing is the front end. So the user, which is a patient or a doctor or an admin, it interact with our three static HTML portals, that is a patient, clinician or admin, which are served by a lightweight Nginx web server. All the user actions are handled by JavaScript in the browser. Next comes is the API gateway. So this is a single entry point for all the front-end requests. There are two major responsibilities of this. First is the load balancing and the second one is the log streaming. Load balancing, it distributes the incoming API requests to different across the different app nodes using a round robin strategy. So here you can see different app nodes, app node 1, app node 2 and app node 3. And the second functionality is responsibility is log streaming. It subscribes to a Redis channel to receive logs from all backend services and streams them in a real time to the admin dashboard. So this is our next another responsibility, that is log streaming. The third tier which we can see here is an application tier. So here we have three identical app nodes. They contain the core logic of the application. When they receive a request from the API gateway, they formulate it into a RPC call and send it to the data tier. They also contain the resilient retry logic, meaning if we have an RPC call to one data node and it is failed, then they automatically try the next one in the cycle. Next is the data tier. So this is basically the heart of our distributed system. It consists of three stateful data nodes. Each node has its own SQLite database. So there are major responsibilities of this data tier. The first is the RPC server. It handles the incoming request from the app nodes. Then we have maintain a quorum consistency. So we need to replicate all the write operation to its peers and ensuring a write is only confirmed after a majority of nodes have saved the data. In our case, that W is equals to 2 because we have a 3 data nodes. Then we have also implemented Makava's mutual exclusion algorithm. So it is participating in the distributed locking protocol to ensure that the concurrent write operations are serialized and do not corrupt the data. And the fourth responsibility is the Berkeley clock synchronization. Participating in clock synchronization protocol to ensure all the timestamps are consistent across the distributed database. So this is the main functionality of our data tier. And the last comes the Redis. This service acts as a high-speed message bus and cache. First responsibility function is pub sub for logging. It provides the publish subscribe channel for a real-time logging system. And it also provides caching. It is used to catch the frequent ready heavy queries like user login data so that it will reduce the latency and the database load. Now this our architecture, it ensures that there is a high availability, fault tolerance and data consistency maintained, which we will be demonstrating now. So now let us see the demonstration of the project. So this is our distributed EHR system. So the objective was to apply the core distributed system principles so that we will build a reliable and fault tolerant EHR system. So our entire 9 service architecture is defined in this docker compose.yml file, as you can see here. And when I run this command docker compose build, so you can see in the terminal logs, the Docker is orchestrating the startup. It's building a Python services. It's starting the Redis. It is launching the data nodes. It's launching the app nodes and the gateway. This ensures a stable and predictable startup. So once all these logs are settled, all our terminals are open and now we can navigate to our HTML portals. Now here you can see that this is our patient portal which has a function to register and also sign in the patient. Similarly for clinician portal we have registration of the clinician and sign in. Similarly in the admin dashboard you can see now there are Uh, Here are real-time system logs and how many total patients are registered, total registered clinicians, what are the active nodes, etc. So now I have already registered 2 clinicians here. So I will just refresh it. So here you can see that registered clinicians is 2 because I have already registered 2 clinicians. Now let us register a patient here. So the registration process is going on and the patient account is created. Now we'll sign in to the patient account. Once the sign in process is done, here you can see the patient dashboard. It gives us a personal information of the patient such as patient ID, username, full name, age. And then we have some medical history records and option to book the appointment. Now the clinician also will sign in to the clinician which I have already registered with. So this is the clinician dashboard. Here you can see that the clinician can submit the new medical record and he can also view the query patient records. And he can also see the what are the upcoming appointments. Now once we see the in the admin dashboard, we can see that all our requested such as we have login. So here we can see that attempting RPC login to data node 3. Then executing the login read operation. Since it is a read operation, we don't require any log. Then RPC login to data node 3 is successful. Then when you are attempting to get the appointments, it is going to data node 2. This means that our API requests are sent to data node 1, data node 2, data node 3. In this way, we can see the loads are balanced among the all the 3 nodes. Also here you can see that periodically clock synchronization is taking place. This means a Berkeley algorithm is getting implemented. So here you can see that the data node is a master node, data node 1, which is a master clock. It is starting the clock synchronization and an average offset is sent periodically. So that clock synchronization is maintained through all the terminals. Now we'll see the workflow of our EHR system. So once I go to the patient portal, here I can see the patient ID. Now a clinician can write a clinical note such as, for example, fever and prescription is take dolo. Once I create this record is submitted and this should be visible in the patient portal. So on refreshing, I can see that Dr. Rahul Sharma has given us some medical history. Now here you can see the time, that is 11:48 seconds. And once when I query this record, here also you can see the same time. This means that Berkeley's clock synchronization is taking place. And when I go to the admin portal, here I can see that all the tasks are getting executed. That is executing get records, read operation, then get records by UID to data node 3, then get appointments to data node 1. So all the RPC tasks are getting assigned to different data nodes. Now let us demonstrate about the book new appointments. So once a patient books new appointments, he gets an option to select the clinicians. Now we will just select a date and we'll confirm the booking, and the booking is getting successful. Now in the clinician, we can see that once we refresh it, we can get there is upcoming appointment from a patient and it is booked. So this is the main workflow of our system, EHR system. Now let us go to the next part. So the other task is the RPC and the load balancing. So here I will demonstrate it with just I will refresh the patient registry. And here you can see that RPC get all patients, it is sent to the data node 1, and you have loaded one patient and two clinicians. Similarly, once again if I refreshed it, here you can see that RPC get all doctors and patients, it is sent to data node 2. First it was sent to data node 1, second it was sent to data node 2. Again I will refresh, now it is sent to data node 3. So this means that our load balancing is maintained and it is following a round robin strategy. So when I refresh the patient registry, the API gateway receives the request, and using a round robin strategy, it forwards it to the different app nodes each time, 6001, 6002, and then 6003. So this is known as a load balancing. The app node then makes a RPC call to data node to fetch the data. Now we'll move to the next concept, that is our quorum consistency and Merkabah's mutual exclusion. So with a write quorum of 2, our system must tolerate one node failure for all operations. Now currently, as you can see, the active nodes are 3. Now I will just stop or one of the node, and even if one node fails, my system should work correctly. So I will just go here. Here our EHR system is running in Docker, and here I can see the 3 data nodes. I will stop any one of the data node. Now as you can see that data node 2 I have stopped and it is now offline. So once I refresh it, I can see that now active nodes have become 2 out of 3. So as you can see here, the failed to get time from peer 2 because the data node 2 is now stopped. So RPC to that data node 2 is failed. So no address associated with the host name. So it is retrying. So it means that now one of the data node is failed. Now even if my one of the data node is failed, I should maintain a quorum consistency with other two data nodes. So here, if for a same patient, let's say patient ID, I will write another clinical note. For example, body ache, paracetamol. So once I create a record, the record should get created even if one data node is failed. So let us see. As you can see that the record is created successfully, and in the patient portal, once we refreshed, we can see that there are two records and the record of body ache and paracetamol is visible. Similarly, if we book a new appointment through a patient, so loading the clinicians here. Yes, so if we confirm the booking here, so you can see the appointment book is successful. And when we see the in the clinician portal, so the upcoming appointment is getting reflected here. So this means that even if my one node is failed, the operation was successful. So the system is fully fault tolerant. Now let us see the logs out here. So data node that handle the request. Here you can see that it has initiated a Makaba's lock. So once the locks is initiated, as you can see here, sending lock release to peer 2, sending lock release to peer 3, RPC book appointment to data node successful, receive appointments successful, lock is acquired, and also you can see here quorum write completed with 2 of the 3 acknowledgement. This means that our quorum consistency and Makeba's algorithm is implemented properly. Basically, what it does is it sends lock request to its peers, receives the reply from the active nodes, and correctly time out on the down nodes. Because it only needs a majority of votes, it successfully acquired the lock. So it then performs a quorum write. It wrote the data to itself and replicated to the other active nodes. Since it received 2 acknowledgements, the W is equal to 2, that is quorum, write is equal to 2, was satisfied. So this proves that our system remains both consistent also and available also during a partial failure. And we have also implemented a deadlock simulator. So once we simulate a deadlock, there is a deadlock initiated. And deadlock is detected and resolved via a timeout. So what is the core logic of this deadlock simulator? We'll just see in the code. So in this, we can see that two doctors are attempting, Doctor 1 attempting to add record for patient B and Doctor 2 attempting to add record for patient B. So the script simulates that there are two doctors trying to write records for patients in a conflicting order. As you can see in the output, one request succeeds while other times out. This is not an error, it proves that the locking mechanism is serializing the request instead of deadlocking. Thus, the system stability is maintained. One more functionality I would like to show is the data replication. As you can see that here we have maintained three data nodes, node 1, node 2 and node 3. And we have maintained a SQLite database. So once we log in, whatever transactions we do, all these are stored in all the three data nodes. So as you can see here, I have opened the data node 1 database. So here in users, you can see that we have a 3 users. Similarly, if I open another data node, that is data node 2 database, here also in the user sections, we can see that there are 3 users. Similarly, uh, you can see in the appointments, we have created one appointment. So here it is reflected. And if I open another database, that is data node 1, here in the appointment section, you can see 2 appointments because the data node 2, in data node 2, we have stopped that data node. So only one appointment was reflected because the data node 2 was not available at that particular time. But data node 1 and data node 3, these two were available when the data node 2 failed. So in data node 1, we can see 2 appointments, and as well as in data node 3, we can see there are 2 appointments. So here we have maintained the data replication. In conclusion, our MediSync Pro project was successfully implemented all the 8 required tasks. We have demonstrated a resilient distributed EHR system that ensures the data consistency through quorum, manages concurrency with fault-tolerant backup implementation, and remains highly available through load balancing and robust error handling.